Today, I'm going to take questions at the end of class in this one. I want to get through this one topic. Now, in Dr. Wentworth's book, we've done signal, we've talked about grounds, we've done shields, we've gone through basically the EMC section. We've even talked about filters, right? I didn't cover the insertion loss and return loss formally, but I'm going to tell you most of the stuff in that section is very, very straightforward. Now, when we talk about insertion loss, it's IL. Oh, come on. These are brand new, too. So much for brand new. What's going on? Yeah, but the problem is if they're dried out. We'll go with this one for now. Let me just try this. Try these two. All right. Back to insertion loss. IL is 20. This is going to be times the log of the magnitude of the signal at the output with no filter divided by the signal at the output with a filter applied. That's what insertion loss is. It just means how many dB of attenuation are you going to incur with and without a filter. Now, I'm going to go through this straightforward. And the problems are easy. Doesn't matter what the circuit looks like. I'm going to pick one. Suppose this is my circuit. I have a resistor R, another resistor R, right? Here's my input, and I'll literally call it plus to minus Vn here. And this is my output. I'll take you through a problem and you'll see this. Now, there's no filtering here. I'm just using two resistors to show voltage division. If you look at this, I can say V out is simply equal to really V in, right? And then it's times R over 2R, right? Or really it's just V in over 2. Do you all see this, class? This is simple voltage division. All right. Now I'm going to put on my filter. In this case, I'm going to choose the simplest possible filter unit. It's just going to be a capacitor. This is without filter. This is V, no filter, however you want to designate it. Doesn't matter how you do it. I'm going to put in a filter by only adding one element. And you can add many elements, but this is one element. Now remember, you have to get the output without a filter present. That's the idea. Got it? Now we add a filter. The filter I'm going to add is a capacitor here. I could add a capacitor here. I could put an inductor in series. I could make it as complicated as I want. But now I'm going to get the output with the filter elements added. Everybody understand that? When I do this, I can see that this has an impedance right here. And the capacitor has an impedance of 1 over J omega C. Does everybody agree with that? Right? And the resistors are still there. So when I look at this output leg here, I can call that ZRC. And I can say that's equal to 1 over R plus J omega C. Does everybody understand what I've done there? I took 1 over the first impedance plus 1 over the second impedance. Everybody got that? And you could use S instead of J omega. It doesn't matter as long as you understand what the designation means. Now we have that. Now that I've got this filter element in here, just keep watching, I can say that V out over V in, right, would be equal to simply this impedance, which is ZRC over ZRC plus R. Please just take a look at that and make sure you see that it's simple voltage division, isn't it? So V output here will just be this times V in. I'm going to put V in last, but I want to focus on what the filter output will look like. Do you all see this? Now, I know it seems trivial, but people blow this one. Just keep watching. And that's the reason I chose it. So I'm going to divide top and bottom by ZRC. Now, I've done this kind of problem many times, and I know what you like to get is the output impedance in only one term, all right? And so I've got three possible terms, 1, 2, 3 here. It's in 2 of the 3. If I divide by ZRC, it'll be in just 1. Do you all see that? When I do that here, I'm going to have 1 over 1 plus R over ZRC. All right? Now, after that, I put in what ZRC is, and it's 1 plus JR. And ZRC is this. Well, 1 over that is just 1 over R, right? Pardon me, there's no J here. Yeah, that's just R. I'm sorry, I put a J there, it shouldn't be. It's R plus 1 over R plus J omega C. Please just take a look at this. Make sure you see every step. It's obvious, but people can overlook it because it seems so simple. Do you all agree with that? All right. Now what happens? At this point, you can see what happens is R times 1 over R becomes 1, right? And I have 1 plus 1 is 2, so I have 1 over 2 plus, and then it's just going to be J omega R times C. Agree? This is very easy. So easy that people mess this up. Somehow that 2 mysteriously vanishes all the time. It becomes a 1 miraculously. I'm not kidding about that either. Now, when I look at this, I can see my V out is simply equal to 1 over 2 plus J omega R times C times Vn. And then when I go ahead and get my insertion loss, and I'll do it right here, my insertion loss becomes 20 times the log of the magnitude of the output voltage without the filter, which is 1/2, right? Over the magnitude of the output voltage with the filter, which is, and I didn't put this right here, right? So that's the output voltage with the filter. Now what does that become? Well, it's 1 over that. You'll notice this has got a V out on it. This has a V out. And 1 over that right there makes this 2 plus J omega R times C. Everybody agree? I'm just going through the motions. After I state what it's defined as, I need my filter output without the filter, then the filter output, or I should say circuit output without the filter, then the circuit output with the filter. Do you all see this? Make sure you do. Yeah.
What's JL stand for?
Pardon me?
What is it? That acronym right there?
This is J omega RC.
And what's the 21?
20 times the log. I'm sorry if you can't read it.
The one in front of that?
That's a magnitude.
Yeah.
That's 1/2, right? Because the first one, V right here, was 1/2 V. Huh?
Sorry. It's 1 in V.
1 V. The voltage right there with no filter is 1/2 Vn, right? And then what you can see happening is, or I call it V out. I'm sorry, I call it Vn.
Okay.
Vn, my bad. What I'm going to say is this will always cancel. The input voltage will always cancel. And that's why normally when I do this, I just get the transfer function without a filter divided by transfer function with a filter. Wentworth's book has the input voltage. That's the only reason I use it here. To make sure if you're looking at his book and my notes, or your notes from what I'm talking about, you understand. But really, you can get rid of the input voltage. Now, when I look at that right there, the 1/2 gets rid of this, and now I can see that this becomes insertion loss. I have a comment about this. It's 20 times the log, right here, of the magnitude of 1 plus J omega RC over 2. With me on that, everyone? Now, if I was to plot this versus omega, matter of fact, we could plot it versus F if we feel like. And usually it's plotted versus F. Normally it's frequency, not in radians per second, but it's in hertz, usually, all right? So please just bear with me here. What I'm going to do, since omega is 2, yeah?
Sorry, is J omega divided by 2 as well?
Well, it's J omega RC over 2. It doesn't matter if you divide the whole thing by 2 or just this. They're multiplied together. Follow me, class? Now, if I replace omega by 2 pi f, you'll notice the 2 goes away, and then this is where it becomes important. I have pi times f right there. Please just watch it. It's trivia to do, but it's easy to miss. Trivia, once you see it, easy to mess it up. all the time these constants start wavering. Now, if I'm plotting that versus really frequency, and I'm going to do it here. If this is versus frequency, typically the way we do it, we're going to put insertion loss here on that axis. And then this axis is really going to be the log of f, but you're going to have the paper take the log. So if this is like 10, this would be 100, this would be 1,000, and so forth, 10 to the fourth. The paper takes the log. In other words, it's a log paper, but it's linear on the vertical axis. But on the vertical axis, it's 20 times the log of that. Now look. When you start out, put a 0 here. If this term right here is much less than 1, it's really the log of 1, isn't it, class? So what is it at 0? Well, it's the log of 1, right? What's the log of 1? 0. It starts out at 0 dB, and this is in dB, by the way. Stays there until what? Until this has the magnitude of 1. Understand? So I'm just going to show you what I mean. This is very easy to do. If I put pi f r c equal 1, that means f is equal to 1 over pi times rc. Now, in the previous thing, when we talked about capacitors and the break frequency, I should say resistors, and the break frequency was 2 pi. Remember that? 2 pi rc? Here, it's not. It's just pi rc because of the design of this filter. Everybody follow me? Class? So I come out here, and whenever this frequency is equal to 1 over pi times RC, that's the point where it starts coming down at what? First, actually, pardon me, starts going up, not coming down, at plus 20 TB per decade. And I got a comment about this. Do you all see that? It's going to start rising at that rate, correct, class? Because now omega, or really pi f times RC is greater than 1. Do you all follow me? And that dominates. And you can just figure this out. Well, when you're greater than 1, call it an order of magnitude greater than 1, really it's the log of just pi f RC, right? And every time you go up by a factor of 10 in frequency, you bring out 1 extra 20. So it's 20 dB per decade. Can you all understand that, class? Everybody? It's hard to see back there. Y'all with me? Give me a show of hands if you are. Okay, good. If you all see this now, then you can say, this is relatively trivial to do that, right? It is. It really is. As long as you understand what's being done. You've got the output without the filter. We add the filter. This is the insertion loss. That's the only thing you have to worry about right now for this problem. Now, filters, did anybody look at the homework I gave you? All right. In my opinion, it's trivial. I mean, there's nothing in there that is any way, shape, or form challenging. It's really not Emag, it's circuits, isn't it? Isn't this basically circuit analysis? It's not true. We're not doing transient electromagnetics or anything like that. What we're doing is simply talking about a circuit phenomena. And you've had filters before, right? Did you have the concept of insertion loss? This is always used. Now, one other thing, loss. If I'm thinking about this, I'm almost thinking, well, this is the filter's response. That's exactly wrong. The actual filter's response goes down, right? Because this right here is going to be a low-pass filter. Just look what happens as the frequency goes up. The capacitor looks like a short circuit. You have no output, right? But because they talk about insertion loss, what we're doing is gauging the amount of loss. That's the reason. It's truly a loss. So in a sense, a positive loss means the output signal is going down. That's what the effect is. Got it, class? Any question about this? Now, any question about the homework at all? I didn't think there were, yes?
On homework 20, we do a question.
Yeah, okay. What is it?
It was 544 alpha, that one.
544?
Yes, sir.
Briefly, can you tell me what it states?
Yeah, I'll pull it up.
Was this the word problems that I gave you just the answer to?
Yes, sir.
Okay. Go ahead.
Actually, it was 545.
It doesn't matter. Whatever it is, what does it say?
Okay. 546. A component is measured and found to have an impedance whose isotopic frequency response is shown. And it gives you a Bode plot of a magnitude and phase.
Uh-huh.
And then it asks you to...
Hold on for 1 second. Here's what he's talking. This is a resistor, by the way. he's got a plot like this.
And it's 546.
What's this frequency?
1.592, 10 to the third.
This one?
That one's 5.029, 10 to the sixth. And then you have a negative 20 drop at the break.
What?
When it goes down, it's negative 20.
Oh, that's all right. This is minus 20 dB. Go ahead.
It starts at 100 ohms too.
Starts at what?
It starts at 100 ohms.
Okay. Go ahead.
And then, do you need the phase magnitude?
No.
Okay.
No.
That's it.
This is a standard thing. What he's plotting really is, this should be 20 times the log of the magnitude of the impedance of a resistor versus frequency. It should be. I'm not sure exactly how it's stated. It's not versus omega, it's versus F, right? In hertz.
Versus F.
Yeah.
Or maybe it's T.
No, it can't be T. That's actually, this is F. See it right there?
Okay.
All right, now, I told you before that what is this frequency? I just happened to mention it. You remember? This is for a resistor. Remember how we model resistors, right? We got a resistor R, we have a capacitor C, and then we have an inductor L. Remember, that's what they look like first order? It's close. This right here, this frequency is 1 over 2 pi FRC. Do you remember me talking about this before? That frequency, and you can prove it from here. You can just write the impedance equation. You'll see that's where it starts falling. This frequency is the resonant frequency, isn't it? Resonant frequency is always, well, normally if it's omega subresonance, it's 1 over the square root of LC, but if it's F, you got to divide by 2 pi. So this frequency right here is equal to 1 over 2 pi square root of L times C. Got it? Now here's the way you do this problem. Since you asked, this is a very straightforward problem. I know R, 100 ohms is given, so that's R, right? Got me? Just go through the motions. You got a calculator, right? It's this fast to do it. I want to know what C is next. Got it? So for C, the only thing I do is this. Since this is that, if I want C right here, I divide both sides by that. I said this is equal to that, and then I go ahead, multiply by both sides by C, and then divide by that number. So I can see that C is equal to 1 over 2 pi, and this is going to be, well, let me do it. Let me write this down. I'm going to have 1.592 times 10 to the third is equal to 1, hold it. I'm sorry, that frequency, I shouldn't have put the F in there. It's 1 over 2 pi RC is this frequency, my bad, is equal to F break for the lower. So it's 1.592 times 10 to the third is equal to 1 over 2 pi R times C, and R is 100, therefore C is equal to 1 over 1.592 times 10 to the third times 2 pi. I'm just multiplying both sides by C and dividing by that number, and then divided by R, which is 100. Now what do you get for a value?
9, or round it up to 10.
Go ahead.
I think it's 1. What did you say that number is?
What'd you get? 1
Microfarad.
microfarad?
Microfarad, yes.
1 microfarad for capacitance. Y'all see how you're going to get inductance right here? We'll do it real quick, just so we do it. So with inductance, I'm going to have to take this equation and set it equal to that, which means I'm going to take 2 pi times this, and then I square it, and then I flip 1 over and I divide by C. So I can say L is equal to 1 over 5.09, or 029, pardon me, times 10 to the 6. It's that number, and times 2 pi. And then I have to square that number right there. And then I divide by C. So I'm not sure, but I'm almost positive you're going to get the numbers they give you. Did anybody do this one? Anybody at all? You did it. Did you get the right answer? This is the method used. You're just getting those two values. Okay?
And then how did you know it was that circuit right there?
Because I put that circuit on the board and that's in Dr. Wentworth's book. This is our this is a circuit, first order approximation of what a resistor looks like at high frequency. Do you all remember this class? This is standard. We put this down. It's in Wentworth's book. Remember, there are three basic circuits you have to have an understanding of, first order, for how components look at high frequency. The first is the resistor. That's the resistor. The second was the inductor. And the third was the capacitor. And all three of them have only three elements. So they're trivial in terms of your understanding. The one thing about them all, at low frequencies, they all look like they should. And at high frequencies, they go bad, right? Inductors look like what? They should look like shorts. It should look like opens. They look like shorts because of the capacitance. Resistors shouldn't change, but they start the way this particular resistor, and I've got it notched down this way, but actually this thing goes straight up, right? Resistors start looking like they're going to infinity, open circuits. That's first order, remember. And capacitors, when you look at them, the way a capacitor is, they're going to go to infinity too. All right. That's these models. Now, back to what I was doing. Did you have another question about anything with filters? The filter homework.
No, sir, that's it.
All right.
We do a quick one.
Which one?
Point 2, point 3.
Is this one in the book or not?
No, this is in your book.
Okay. All right. Doggone it. Someday I'm going to get started. Which one is it?
10.2, point 3. What question was it? 10.22. No, point 2. Point 2.
Hold on. Compute the electric field reflection coefficient for an air-steel interface. All right. We can do it, but it only comes down to one thing: knowing what the frequency is and knowing what mu relative is. This is for 1045 steel. So here's the whole idea with the shield. This is going to be the shield here, and it has a mu relative of 1,000. Now, I think I put that down. This is 1045 steel. Now, this does change versus frequency, but at the frequencies we're talking about, it's about 1,000. Mu relative in the limit as you go to high frequencies always goes to 1 for all materials. Remember that. Mu relative here is 1,000. It's a lower frequency. But mu relative will asymptotically approach 1 for very high frequencies and very large magnetic field values. At least the concept of mu relative will. Now that's mu relative. The other thing is the actual sigma for this typically is given as sigma of copper times a multiplier. Well, the multiplier is 0.1 if you look at that table. Did anybody look at that table? All right, the multiplier is 0.1. Well, the conductivity of copper is 5.8 times 10 to the 7th. Times 0.1 is 5.8 times 10 to the 6th. Do you all follow me on this? So this is going to be 5.8 times 10 to the 6th. Next, you have to know, and this is air over here, by the way. It's coming from air. And a waveform's coming in, right? Now, air has an eta naught of just 120 pi, right, ohms. Here, we need to get eta naught, right? Now, I told you a trick. If you compare omega times epsilon relative, it's much, much less than sigma. Do you follow me on this, class? Y'all remember this, me talking about this? So when we look at eta shield here, I mean, we can actually do the whole formula for this. You have calculators and that can do this. Does anybody have this on like a MathCAD thing where you can just plug things in and out of a formula? Well, I know eta shield technically is equal to what? Square root of J, right? Omega mu relative mu naught. Now remember, mu relative is 1,000 and mu naught is 4 pi times 10 to the minus 7. Divided by sigma plus J omega epsilon relative for steel is about 1, if you look, right? Times epsilon naught. So that's it. And what he does is he said he wants the reflection coefficient, is that right? Just tell me.
Yes, he wants the reflection and then the transmission
Coefficients, all right? Well, these are pretty straightforward because reflection coefficient is equal to eta shield minus eta naught over eta shield plus eta naught. Technically, the transmission coefficient is 2 eta shield over eta naught plus eta shield, right? These are the formal ones, right? Or you could put it as just 1 plus reflection coefficient. Do y'all agree with that? Now, the thing is that reflection coefficient is going to be darn near 1 or minus 1. And the problem is if you do rounding errors, if your calculators aren't set to take it out, to do, 6 or 7 orders of precision, in other words, you can't round that just up by 1 or else you're going to get a wrong answer. For this one, when you do it, what do you get? Well, first, what are the frequencies you want it for? Just tell me.
30 megahertz, 100 megahertz, and 1 gigahertz.
Let's start with 30 megahertz for just kicks, all right? At 30 megahertz, eta shield's going to have a certain value. You can tell me what it is? I can't do that in my head. Anyone? Tell you what, you don't have to tell me. After you get that, save that number and do this calculation, this calculation. How's that? You don't even have to tell me. Just give me these things. And we can get it in dB too, right? We can take 20 times the log of the reflection coefficient is called the return loss. And then 20 times the log of the transmission coefficient is the insertion loss. But for now, let's just, you tell me what that is. Do they want the reflected losses or the reflection coefficient? Okay, what is it?
I got 1.02 plus 0.02J, but...
Now, how about just get magnitude and angle, if you don't mind? It's about -1. It's about -1. Matter of fact, I think. What did you get? About -1? At what angle?
About
1? No, eta shield's very small, right? Look at this. If eta shield's very small, eta naught's very large, that's a negative number. It should be about -1. Just check that. What's that?
Well, I'm saying if the calculator's outputting 1 at an angle of 180.
Oh, did you say at 180?
No, it's just asking.
What did you say that?
said it like 0.018.
What is it?
I didn't ask the question.
The magnitude is 1, but the angle is 180.
That's right. That's -1. It's about -1. They're all about -1. What about transmission coefficient? Now, do me a favor. Do this right here. Take 2 times eta shield over eta shield plus eta naught. And I'll give you a tip. You can do this. You can get rid of eta shield. Right down there. It's 2 eta shield over eta naught. What do you get? Eta shield's very small. What was it, if anybody calculated?
0.2.
Yeah, kind of small compared to 120 pi, which is about 377. Right? That's the point I'm trying to really enforce in you. Make sure you see the relative magnitudes. There's 2 orders of magnitude difference, at least 3 actually. But you need to use this equation. Don't do this if your calculators, for whatever reason, aren't set to a high precision. What do you get for that? Is it 10 to the -4th or something? Anybody?
You said it was 0.2, right, for eta shield?
I mean, it's, what'd you get?
What's the answer? Tell me the answer.
1.07 times 10 to the 3.
It was times 10 to the -3?
For
80, the transmission.
for reflection, I have the point, or yeah, about -1, and then the other one is
Now, one other thing, too. This is going to have an angle. All right, what's the angle? You're going to need that angle. Huh?
45 degrees.
Yeah, that's right. That's right. 45 degrees is right. You keep that angle. All right, who asked this question? Okay. These are straightforward things. They're not hard to do, but you have to do the calculations right for the eta values. That's the whole thing. The reason I introduced this is that 1045 steel is common. There's a couple of types of steel. The value of mu relative is a function of frequency, and conductivity to some extent is a function of frequency. So make sure if you're at high frequency and for whatever reason you have to deal with this kind of shielding effect with steel, that you get the values at the frequency of operation. Don't look at just generic values. It's the same with epsilon relative, because in water they say it's 81. Well, it's 81 at certain frequency range, not at very high frequencies. Yes?
You said return loss was 20 log of the reflection coefficient.
Go ahead.
And insertion loss was 20 log of tau.
Yes, but if they're talking about the amount of loss in dBs just from reflection, it's different, remember? And they do in some of them, right? Let me just bring that point to a head right now. That's right the way you do that. But remember before when I said about the total loss, transmitted field versus incident, I said that the shielding effectiveness was equal to 20 times the log, and then I had the magnitude here, and it was really going to be E incident, E incident divided by E transmitted. Do you all remember me talking about that? It's the ratio of the incident to transmitted field's magnitude. Well, when we look at the transmitted field, I said it was 20 times the log here of the magnitude, and the transmitted field will be the incident field. So I'll just put it here so you can see it. There's the incident field. Incident field, then it's times the transmission coefficient at the first barrier. That's where you hit the shield, right? Then it's going to be times the transmission coefficient of the second barrier when it's coming out of the shield. Do y'all remember this? And then it's times e to the minus alpha d, where that's the thickness. Now please, bear with me on this one. I went through it, but if you didn't do the homework on this, it's probably, some of this is a little, you're not really confident. Now this always goes away. The incident field strength always goes away. Now when we break this up, you all see it becomes 20 times the log of 1 minus 20 times the log of all this stuff, right? Please just watch this. You all with me on this? So I'm going to ignore the log of 1. So now I'm going to get minus 20 times the log here of this product, magnitude of tau 1, tau 2, minus 20 times the log of this. Remember, that's log base 10, and that's e to the minus alpha d. Are you with me? Now, please listen carefully to this. This next part is imperative you hear me. This has to do with reflection. So this is the reflective loss. Got it? Everybody? Understand? Because these tau 1 and tau 2 are really related to transmission and reflection, but have nothing to do with attenuation. Do you follow me on this? That's where most of your loss usually occurs. It's right there. Then this has to do with the attenuation loss. And in the homework problems, I ask for both, don't I? So when you're talking about a problem like we're doing here, you're going to have to get the reflection, you're going to get the actual transmission coefficient here. That's tau 1, we calculate. And we need tau 2. Now, do you remember, anybody remember what I said about tau 2? Well, the formula for tau 2, or tau anything, is what? It's always the impedance you're going into. This is when you're in the shield, you're coming out of the shield. Well, what impedance am I going into? Right, eta naught, right? So it's going to be 2 times eta naught over what? Anybody? Eta naught plus eta shield. They'll have the same, for either reflection coefficient or transmission coefficient, the bottom stays the same. If it was reflection coefficient, it would be equal to eta naught minus eta shield. Do you follow me on this, class? We don't want reflection, we want transmission. How many understand that right here? Got me? Now, what do you notice about this? Eta shield is much less than eta naught, right? Ignore it. What is this about? Yeah. And normally, you can just plug 2 right in here. And then plug 2 in here. And then you can see when we do the reflection losses, we need tau 1, which we have. We multiply it by 2, take log base 10 of that times 20. And you're going to see, because tau 1 is so small, that that's going to be a negative logarithm, so it's a positive number. Just do it for me. Tell me what you get. This is a reflective loss, because is this problem asked for that or not?
The next problem.
Is it the same setup at 30 megahertz steel?
20 mil steel, 30, yeah, 30 megahertz.
All right, well, this is going to be the same answer for this part. So, I mean, because the thickness 20 mils goes here. But right now, what do you get for this for reflected loss? Just take that tau 1 that you had 0.00106 times 2, that's a magnitude, and then take the log of it, base 10 log times 20.
Minus 53.
No, it'll be plus, because there's a minus sign.
Plus 53. I forgot the minus.
53?
53.47.
All right, what is the answer?
53.23.
All right, somebody's doing it. There's error in the, rounding error. But that's right. You all see that, class? Yeah?
And so you wrote attenuation loss, but it asks for the absorption loss?
Now that's this. This is a reflective loss.
Yeah, the next one you
That's absorption, or you could say it's attenuation.
Yeah.
Absorption's same thing. You can call it absorption too. What it really means is how much has to do with the signal just shorting out in the actual shield itself. And that's usually not that high. But for this one, here's what you have to do. You have to find alpha. Do you remember how to find alpha? Well, yes, that would do. For this problem, yes, you're right. Technically, you would say what? You would say gamma is square root of j omega mu naught times mu relative times sigma plus j omega epsilon, right? You can get rid of the j omega epsilon, and it does come out that alpha is about 1 over the skin depth. You want to do that part just for the heck? All right, so skin depth is equal to 1 over the square root of pi f mu sigma, right? Now, it's mu naught times 1,000, by the way, right? And sigma was there, which is 5.8 times 10 to the 6th. So now you can get the skin depth, and you can take 1 over that, right? Can anybody give me that? It's very small.
You said it's
Or you can take 1 over that if you want alpha. You can just say alpha is 1 over the skin depth and give me this, because this number will be large.
you said it was 30 megahertz, right?
Mm-hmm. 1 over pi times 30 times 10 to the 6 times mu 0, 4 pi times 10 to the minus 7 times 1,000 times 5.8 times 10 to the 6.
I got 1.5 times 10 to the negative 9.
Anybody else?
I got negative 12 like for alpha.
Anybody else? Remember, there's 1,000 in here too. Remember, mu relative is 1,000. What'd you guys get? Anybody else? Guys, you got to take square root. What?
So alpha's a really large number.
Yeah, and just what is skin depth? Give me one of the two. Anybody?
For alpha, I got 828809.
That's a single number? That's 828,809? All right, fine. If that's alpha, it's fine. Now, D is in mils. So we have to multiply that by what? 2.54, 10 to the minus 5, right? 2.54 10 to the minus 5 times, was it 20 mils? 20 mils. So therefore, the actual D you want to use is 2.54 times 10 to the minus 5 times 20 mils, and that will be in meters.
5.08 times 10 to the negative 4.
Take that, multiply it by alpha, then stick it in here, take e to the minus alpha d. Sorry, it's a little messy. Y'all see what I'm doing, class? This is not hard to see. It's straightforward, but people will mess this up, especially on quizzes and tests. They will forget how easy it is to get alpha. Remember, this is a very good conductor. So what do you get for this? Just tell me what the absorption losses are. First, get e to the minus alpha d. There's a starting point. So there's d, that's alpha. Multiply them, get a product. Take e to that value, Then take the log base 10 of that times 20. Anybody?
Positive 3,657.
Log of that?
That's 20 log.
E to the minus that? What is this number?
That number is.
It's a negative 420.
Uh,
I got 421.
Yeah.
is that right for all right, e to the minus 421? This doesn't sound right. There's something wrong with that calculator.
Different alpha.
Good.
1.2 micro.
1.2.
1.2. Yeah, 1.2.
No, not for alpha. Skin depth, you mean? Skin depth would be that, not alpha.
Okay.
Alpha's huge in this one.
I got that.
What?
I got that.
For alpha? What'd you get for this? Did you get the product of that times that? That's 10 to the minus, that's 10 to the fifth, that's 10 to the minus fourth, that's just 10. There's something wrong with that. Multiply those two together again. That's 5.08 times 10 to the minus fourth times 828809. What do you get? There's something wrong with what you told.
10 to negative 6.
Where? Oh, yeah. You're right. That's my bad. This is 10 to the minus 6, not 5.
I got 51 micro.
What?
2.54 times 10 to the negative 6 times 20. That is 51 micrometers. For D.
Call it minus 5. That's fine. All right. Now go ahead and take that times that. That's better. My bad.
Times.
It's 10 to the minus 6. 2.54 times 10 to the minus 6. We want to go to meters.
Is that a comma? E
Yes. Just one big number.
times that. So alpha times D is 42.1.
All right. Take e to that. E to minus that number
E to that.
with a minus sign.
Minus sign.
Yeah.
A very small number.
All right. Take the log of that very small number.
You were right the first time on mils, it's 10 to the negative 5.
Really?
2.5 times 10 to the negative 5.
Oh, 25.4 times 10 to the minus 6. Never mind. You're right. My bad.
It's not negative 6.
First, times 10 to the negative 4.
All right, look, guys, this is how you do it. That's one thing I wanted to cover. All right, did you anybody get? I mean, tell me what this is. The whole value. Just give it to me. We're playing games here.
3,657.
After you take log of that times 20, what does it say in the answer?
That's the answer.
Well, that much attenuation, there's nothing left. I mean, it's insane. All right. Look, those problems aren't hard to do. Just follow the formulas that I've given you in the method. I need to cover this, guys, so I need to start today. I was going to start about 20 minutes ago, but that's okay. I'm paid to teach, not complain. I wish I was paid to complain. Did anybody go down to LSU? Anybody? Didn't we have members in the band down there? Didn't you go down, Randy? No one went down? I wanted to find out how loud it was in the field, because apparently it was epically loud.
Especially when they did the stop on the goal line.
Only thing I can tell you is when it's that deafening, nobody can hear a quarterback. And you are really in trouble if you don't have some kind of visual key to go off of. And I felt for that young quarterback next, because he was in a world of trouble when he couldn't hear himself think. That's part of the game. Now, this is not in the book. Got it? What I'm about to show you is real EMC analysis that's not in the book, but you'll thank me for it if you ever have to do this in compliance engineering or product verification or anything like this. So I want you to be attentive. Some of you know some of this, some of you don't. Normally when we talk about waveforms that are digital waveforms, they repeat themselves. They have a certain rise time. This is called tau rise. They go to a certain amplitude A. This is a standard clocking pulse. This is where all the EMC problems come from. And this is going to be a voltage, V of t, not a current. Comes over, stays flat, and then it will fall off down to here. This is called the fall time. Almost always, we take the shorter of the two and use that, all right? So we make the rise time equal to the fall time. We find which one is the minimal time when we use that. Now, this repeats itself at t, and then you've got this. It just goes up, stays there, and the clock pulses repeat themselves. What's important to know is this is called the period, or capital T. It's actually the pulse repetition interval, PRI, but use capital T because most of the work so far up to now you've seen capital T for a period. Haven't you, class? All right, now this is the part I got to be clear about. This is the fall time, that's the rise time. We're going to assume they're the same. Go from the center, 50% point here, to the 50% point here and call that tau. Now that's called the on time or the up time. And then you can get something called the duty cycle or duty time. It's used duty cycle equal to duty time, and that's equal to simply tau over capital T. You have seen this before, have you not? Duty cycle is used all the time in digital stuff. Whenever you've had real digital circuits, how many have had Dr. New? When he was teaching you how to do digital stuff, he was talking about duty cycle, was he not? And you did it also in a couple other courses too, plus your laboratory work. Now, when we look at this waveform, do you all agree it's periodic? It repeats itself on and on and on. Anything that's periodic can be expressed by a Fourier series. And this is important you catch this. We're going to use the exponential series. So we can say that my V of t actually can be expressed as a summation from n equals minus infinity to infinity of some c of n e to the j n omega naught t. And here, the fact is omega naught is the fundamental frequency, and that's equal to 2 pi over t. And the value of c of n is equal to 1 over the period. And then it's the integral from any point. I like to say go from minus t over 2 to any point plus t, to t over 2, of the function v of t times e to the j n omega naught t, but it's a minus sign there, dt. Now this is standard Fourier analysis. I'm not going to use f. I know Dr. Tugnate will use f if you're taking communications. I'm going to do it this way because this is the more common way to see this. Do you all see this, class? You all remember it? Now that says that that's periodic. If I did the integration, I could calculate Cn right here, right? This is something some of you haven't seen. If you've had me for signals, you've seen it. Now I'm going to take the first derivative of this signal. So the first derivative of this signal, we'll do this. When I take just V prime of that signal, right here, now what happens? Well, from here to here, I have a constant slope, right? So the rise is a, the run is tau rise. It will be a constant value here of a over tau rise. It will stay there until I hit tau rise. Then it goes to 0. Then it'll keep going here. And once it hits this point, which happens to be, by the way, tau, it's another reason they do this, it goes from there downward, so it does this until it hits this point. And that point is literally tau plus tau rise. And then it repeats itself. Here, it'll do the same thing. I'll give you some notes on this, but you can see it basically is going to repeat itself. Oops. Goes to 0, and then right here, then it goes negative as such. Do you all follow me on that, class? Now, what is that? Well, that's the derivative of this. Please watch this last point. I don't have time for all of it today. Now I'd say V prime of t would be equal to the summation from n equals minus infinity to infinity. But I'm taking a derivative of that with respect to time. Well, what happens? Some of you know. You've had me. Does C of n have a time-varying component? What's the derivative of that with respect to t? Just jn omega naught. That's exactly right. So I have C of n times jn omega naught times e to the jn omega naught t would be that series. But you'll notice I don't have a constant there. I have a constant times jn omega naught, right? But what I can do is say this constant right here, we'll just call, whatever that is, we can just call this Cn prime. Follow me? And now that fits the form of a Fourier series. A Fourier series says we have constants here that are functions of n, right? What I've done here is say I have a constant that's actually the first constant, a function of n, times another constant that's a function of n. In other words, it's a function of n, right? What is that coefficient going to be? Now it's going to be c of n prime is simply 1 over t, and it's the derivative of t right here from minus t over 2 to t over 2 of e to the minus j n omega naught t dt. Now that coefficient is that coefficient. And you see it's related to the Cn we want by simply dividing by Jn omega naught. Do you all see this, class? Some of you haven't had this. And then I take a third derivative, and right now I'm out of time. Listen now, second derivative. The second derivative will give me an impulse there. Will give me an impulse here that's negative. Give me another negative going impulse, and then a positive going impulse. I'm going to stop there. That's what I wanted to start with today. And I'm going to give you some reading. I'll give you a few pieces of homework that you're probably, those that have had me will just probably do it well, and those that haven't will struggle. But next time I want to bring everybody back together and do this. This is really MC analysis. We're going to apply this thing for circuit analysis purposes, and you'll see that this is valuable. Most of the time you don't get this until you get your senior level courses. What's that? Okay. All right, see you Wednesday. We play Ole Miss next.